So let me briefly introduce Nazmi Burak Budanur to you. He obtained his bachelor in Istanbul Technical University with a double major in electronics engineering and engineering physics, and continued his master's again in Istanbul Technical University. He obtained his PhD in Georgia Institute of Technology uh, under the supervision of Predrag Cvitanovic. I hope I'm telling this right. During his studies, he worked as a teaching assistant and research assistant in various universities. Now he's a postdoc in IST Austria. He continues his research in nonlinear dynamics and turbulence group. And in his website, he says his research interest includes various problems that involve fluids, such as low rate turbulence, transition to turbulence, and pilot wave hydrodynamics. Welcome again, Brad. Screen is yours. You can start whenever you like.
Thanks a lot. Okay. So I have 45 minutes, right?
40 minutes plus 10 minutes questions and answers,
okay.
But we can extend it to 5 to 10 minutes.
Okay.
It's all right.
Okay. Perfect. Okay. All right. I'll use it effectively.
Thank you.
Okay. Thanks a lot. So I had the feeling that I'm a little bit of an outlier in this workshop, but until yesterday, I saw Alex Kontorovic's talk where you have already seen measures in phase spaces, which for that talk, the surprising thing was that non-uniform measures were seemed like they were surprising, whereas as I will tell you in my talk, usually in systems that we consider uniform measures are exception almost. And then but nevertheless the title has tangles and loops, but today I will be talking about classical fields. Okay, everything will be completely classical, no quantum, and so let's go. Okay, but before I begin, I should of course thank the people who did the work actually, one person. So all the results that I'm going to eventually show you in this talk were calculated by Gökhan Yalnız, who started working with me when he was doing his master's at Boğaziçi University, and now he's a PhD student at IST Austria. And calculations were actually done on these computers, Truba in Turkey, and then IST cluster here in Austria. Okay. So I'll be talking about turbulence, and I have seen in various places this expression, turbulence is the oldest problem, unsolved problem in physics. Is the title of this very nice popular article on Ars Technica. And, and it's almost nearly ignored in physics departments at this point. And maybe the reason is because Heisenberg scared everyone. So he said, when I meet God, I'm going to ask him two questions: why relativity and why turbulence? And I really believe he will have an answer for the first. So Heisenberg, and actually there's some dispute whether this quote is actually said by Heisenberg, but okay, so somebody said this, and then they felt like turbulence is a very desperate problem. Okay, and but let's try to define it. What is turbulence? And usually turbulence for most people is some exciting part of a flight, but it is actually almost most fluid flows are actually turbulence. And then it was recognized by Leonardo da Vinci, and in these drawings of his, where you can see, I guess he's drawing streamlines where there are some swirling motions in the fluid. And then here there is another experiment where they are releasing some colored smoke from the ground, and then the airplane passes through it. And as you can see, there's big vortex, some large coherent motion, and then some more stuff is happening around here and so on. And here's an example from how it looks like in a lab. This is a video. This is a measurement taken by a colleague of mine, I think Michael Riedel. It was done in the lab at IST Austria. And as you can see, we have a glass pipe, and in the glass pipe there is water flowing, and then in the water there are some tiny particles that move with the water, and you shine light on this glass pipe and you see that things are moving erratically. So it's not a straight fluid motion. There are little complicated motions going on. Okay, so these are sort of examples of turbulence in various settings. And somehow, okay, I'm having a technical problem. Let's see. For some reason, my slide won't switch to the next one. Okay, this is where I would like to be. All right, so mathematically, we need a definition. And then in this talk, turbulence will be some chaotic fluid motion governed by these equations. These are Navier-Stokes equations. And then we'll just go through what these terms mean by one. First of all, we have density, and then the field that we will be interested in will be the velocity field. So this is U is a vector field that tells me the fluid velocity at a position x, y, z at time t. And then we have another field that's the pressure, and its gradient shows up as a force. And then there's viscosity. So this is the term where the trouble comes from, because this makes the system dissipative, of course. And then there's another force term for the body, external body forces, and that's here. And okay, so I just rewrote what density is here to have a letter M. And then this whole term is essentially the acceleration of a fluid particle, and you get this extra convection term because the fluid is moving. And right-hand side is essentially all the forces. So what we're looking at is just F equals ma, okay, for a fluid, and it's dissipative. So what can you do with this equation is you can actually solve these equations. Okay, so this is part of a lot of engineers' life, where you have a problem, this geometry, and there's governing equations of motion, usually some approximation to Navier-Stokes equations, and then there are some parameters, presumably, and you put it on a computer like this one, for instance, and then you measure what you want to measure. And you might be interested in some convection problem, for instance, or you might be designing a car or a spacecraft. There's a fluid dynamics problem somewhere. You can simulate it and you can get your results. Now, at this point, you might be thinking, we know the equations, we can solve them, and what's the problem? Okay, so maybe there is no problem. Well, I'd like to claim that the problem is that there's no understanding in this story. Okay, so the simulation is a black box, and I'm using the term in the same sense as it's used in the context of, say, artificial intelligence. It tells you something because it has so many degrees of freedom. It did a calculation and then gave you out an answer, but there's no, it's not immediately available for you how it got to that. Let's say it's not interpretable. Okay, and the reason is simply because there are too many numerical degrees of freedom. So in typical turbulence simulations, there is at least 10 to the 5 degrees of freedom that come from spatial discretization, and I can guess that there are even more in these pictures that I took from Wikipedia. And then there are long-range correlations, coherent structures, and so on. So the usual approximations that we are sort of familiar from physics are not very useful. So I'll try to convince you that having fewer variables to describe these kind of systems can improve our understanding of it fundamentally. And the sort of idea I have in mind is very similar to what was articulated by Anderson in 1972 in this article, More is Different. And I will give an inaccurate summary of that article here for you using an example. Okay, so example goes like this. The idea goes like this. You have on the right-hand side the, public transportation map of Istanbul with, metro and trams and so on. And this is built by humans. Okay, so here is a model of a human. And then, but it is not immediately obvious how humans came to this place. And if you were to do a theory of, public transportation based on a theory of a human, that might take a very long time to get there. And that description can be significantly shortened if you introduce trains into conversation. Although I later realized that Istanbul has this Metrobus lines in it, and it's, but this story is still there. If you have trains, you can have some framework where the public explaining public transportation becomes much easier. And I think the problem is very similar in this context, which is, we have the Navier-Stokes equations, and they locally tell us, there is momentum conservation. But when we look at this picture, it feels like there's more to that than the momentum conservation. And that's what we are we are going to be looking for. Okay. And it would have been great if we solved this problem once and for all for everything, which is not the case. But today I will be specifically talking about one turbulent flow, which is called the three-dimensional Kolmogorov flow, described by this Navier-Stokes equation here, which we have already seen. And in this form, I have non-dimensionalized everything and introduce kinematic viscosity. Okay, so I don't have density anymore. And then on the right-hand side, as a body forcing, I have this sinusoidal forcing term, which is depicted in this picture where I'm pushing the fluid in the lower half of my simulation domain in one way, and then upper half I'm pushing it the other way. Okay, so and the domain is a rectangle, and it's periodic in all three directions. So this is a rectangular domain, and it's periodic, and fluid is incompressible, so it's divergence free. Okay, so its divergence is 0, and this system has one simple solution that you can find analytically. That's called the laminar solution. It looks like this, and it just happens if the velocity field is aligned with the forcing term here. Okay, and then the solution is actually stable, so linearly stable, which means that if you start on this solution, you remain on this solution, and you don't, so beginning on a laminar solution, the system doesn't go anywhere else, but then you can have a perturbation in the system, which you can imagine as a noise. Okay, so some perturbation you can apply as an initial condition in your simulation, let's say, and then you can observe turbulence. And this is a typical scenario in most fluids that people are interested in experimental studies as well, the fluid flow in a pipe or fluid flow in channel at low Reynolds numbers, which is for the sake of this talk, imagine as the low speeds fluids can be laminar and turbulent at the same time, and turbulence requires finite amplitude perturbation to be observed. So as I said, we can simulate these equations, and I will go through how do we do that in this 1 or 2 slides. And so we have a code to do that, which you can download from this address soon, not right now, but we will publish it sometime, definitely in the next year. So let me show you the Navier-Stokes equations once again. And this is the term where the trouble comes from, because it's nonlinear, as you can see. Okay, so I just gave it a name. It's a nonlinear term from now on as a shorthand. And then if I take the divergence of this equation, I get an equation for pressure. Why? Because the linear operators just the linear velocity field terms goes to 0 because the velocity field is divergence free. Okay, and then I get a Poisson equation for pressure, which is soon you will see we can solve numerically. And next thing I'll be doing is introducing the Fourier transformations, because domain is asking for it, right? We're periodic in all directions, so Fourier representation is an appropriate basis for this domain. And then write my equations in the Fourier space, which is actually already looking like something that you can put on a computer, right? Because I get an equation, time, the partial derivative of time for every Fourier mode, and the right-hand side is a function of all the Fourier modes. So let's rewrite everything compactly by introducing what I'll be referring to as the state vector. Okay, so I have this vector psi where I have all my numerical degrees of freedom, which are going to be, you know, real and imaginary parts of the Fourier amplitudes. And this is a very large vector, and, you know, it's formally infinite dimensional, of course, but here we are always going to be dealing with the computational settings. So this is the vector that is about more than 100,000 entries. Okay, so it's a large vector, but using this definition, I can express everything as an ODE, and that's all an ordinary differential equation. So this is helps me to compactify my notation. Okay, but you know that underneath this, there is a Navier-Stokes equation. All right, the next thing I'm going to introduce is what's called the finite time flow. And this is kind of an unfortunate term at this point, because this flow is not fluid flow. This flow is flow in the state space of the system. Okay, so, and it's just a mapping nonlinear operator that maps your initial state to some state after time t, which comes from your simulator essentially. And then finally, I need a state space, which is a subset of this very high dimensional space. And state space is the space of all possible fluid states. And so every state that I can find in the system is an element of the state space. Okay, so with these definitions, I can now say I have a dynamical system, and because there's a state space and the flow pair gives me a dynamical system. And this gives us a sort of different geometrical view of fluid dynamics in the following sense. So you can imagine time evolution of a fluid as a one-dimensional curve in the infinite dimensional state space of the system. Okay, and what it means is just some, here's a sketch of that, where I have the initial condition, and then my simulator, which sets the finite time flow, is acting on my initial condition, and as a continuous parameter time. And so I get a curve as the set of states that I observe. And the strategy that I will be following is to sort of try to understand the geometry of this space in order to simplify the description of the fluid. And so let's start with some explorations, and I hope you're seeing this video on my screen. Now, this is actual data that came from a simulation of this equation. And then on the right-hand side, I'm just showing you some isosurfaces of the velocity field. These are isosurfaces of the velocity in x direction, so red and blue. And then purple and green are the isosurfaces of the vorticity, okay? And also in the x direction. And then on the left-hand side, I have a state space projection, which is a projection of this curve that I sketched in the previous slide. And axes in this projection are some some directions in the state space that capture high energy fluctuations. What you should keep in mind that the actual evolution happens in the infinite or very high dimensional state space, but here we're just looking at a projection onto three dimensions. But even in this projection onto three dimensions, it's already very, very complicated, right? It's quite a mess. So these are the parameters that I use in this particular simulation, which will be constant throughout this talk. And then on top of that, we had some symmetry restrictions, and this is these restrictions confine the dynamics in a subspace where the flows have certain symmetries. This is a trick that's usually done by the theorists who studies problems like this, where in this case, they mean that the lower half and the upper half of my computational domain are the same. Also, there's like a left-right symmetry. Okay, so this reduces the degrees of freedom that the system actually has. But the dynamic still has the same characteristic, which is, as you can see, it's very complicated and it's actually chaotic. And then the turbulence is transient, so eventually it goes to laminar. But let's first focus a little bit on what chaotic means, okay? And here are my first of two slides on chaos, and this is the definition of chaos given by Edward Lorenz. He said, when the present determines the future, but the approximate present does not approximately determine the future. And we'll soon see what does this really mean. But Lorenz came to this conclusion by studying these equations, which are known as the Lorenz equations. And these are, this is, by the way, it's not first example of chaos by no means. Chaos was chaos was known in the Hamiltonian systems since a long time, although it wasn't called chaos then. Lorenz didn't call this chaos either, that comes later. But the significance of Lorenz's paper is that this was a dissipative system, okay? So it's not a Hamiltonian system, but in a dissipative system, he observed chaotic behavior. And I sort of introduce our own notation here. Psi dot equals to V of psi. We have a set of ODEs. And what Lorenz did was fairly simple. Well, at the time it wasn't simple, but now it's very easy to simulate these equations. And then I did a numerical experiment similar to Lorentz, where I start two simulations with initial conditions that are very close to one another. Okay, so here I have psi 0, and the other one is some three-dimensional noise times 10 to minus 4. So these initial conditions are pretty close to one another. And I started integrating these equations, and I'm showing you here one of the coordinates as a function of time. And what happens after some finite time is that these solutions don't look like they're related at all. Initially, they seem to follow the same trajectory, but after some time, all of a sudden, they go all over the place. And this is what he meant by approximate present doesn't approximately determine the future. Why? Because after some time, any present is the same, more or less, because there's tiniest noise go so high that predictions are completely useless in a way. And of course, Lorentz was motivated by weather. So this directly applies to weather prediction, because you can never measure your initial condition with infinite precision. And since your initial measurement of the initial condition has finite precision, you can never predict weather, next year. That's not available. Okay, so this is usually how people show the Lorentz attractor. It's called a strange attractor because you take these equations, you integrate them, and then you project on your solution onto a three-dimensional graph like this one, and you see that the dynamics is confined to a volume. Okay, so it's not going to infinity. It's like it's always in the same area, but also it never repeats itself. There's no periodicity. It's not stationary. It keeps going around and never coming back to where it started. So that's why it's called a strange attractor as opposed to a normal attractor. And I'll show you some. Here's another projection of that strange attractor on two dimensions. And here are different set of solutions. Okay, so if you look closer to this object, what you find is that it actually has, it actually has periodic solutions. Okay, and the periodic solutions seem to be embedded in this strange set. They are not far away from there. There are periodic solutions, but they're all unstable, so you never see them if you just run your equations. But of course, there are methods to compute them, and I'm pretty sure there are methods to also prove their existence. But the point that I would like to make here is only that these solutions look like the chaotic solution. Okay, just qualitatively take this statement for the time being, but they are finite. So they are these objects are not infinitely long like the chaotic solutions. They are loops, so they can be useful. And this was the sort of basic intuition why people looked at periodic solutions in turbulent flows, and all numerically, of course, like these systems, there are not many things to do analytically. And I'm showing you an example here from our work, the three-dimensional Kolmogorov law, where we have a periodic orbit that is this orange closed loop here. Okay, so this is a periodic solution that we found numerically, and I'll come to how do we do this. And then here's a turbulent trajectory. Once again, this is a state space projection. You should always keep in mind that this is a projection from infinite dimensions. And then the observation that I'd like you to make is that, when turbulent come close to this periodic orbit, first of all, it seems to be coming close to the periodic orbit. Secondly, they have some similarity to these curves. These projections look similar. And here are some references. This is the pipe flow is where I started looking at these things, and then people looked at these solutions in different systems. And But now we're talking about the 3D Kolmogorov flow, and I'll show you how do you actually find these, just sketch out the steps to do so. Okay, so how do we actually find these periodic orbits is it starts like this. Normally when you just when you just simulate a turbulent flow, you don't have periodic orbits, so you just have turbulent flow. So I sort of deleted the periodic orbits from the picture in the previous slide. And then if you just have the turbulent flow, how can you even begin searching for periodic orbits? And the way you do it is by looking for the recurrences in the chaotic time evolution. And you can measure those with a function like this one here, which basically looks at the difference between the state at time t and then state at time tau later, then normalized by the norm of the state at time t. So in this norm is all choices are almost equally valid. Usually everyone just uses the Euclidean norm in the state space. Okay, so and the idea is that if you're close to a periodic orbit, this recurrence function should have a minimum because you're approximately coming back to where you started. And you can visualize this recurrence function in a plot like this one, where the color represents, red is low and blue is high. So for example, maybe this is a closed recurrence. And what you do is basically find and basically start Newton searches. And this is very similar to the Newton method that you saw in computational physics class, let's say. And you start a Newton search for the roots of this function, which is the definition of a periodic orbit, basically. And then for initial condition, you use these local minima of this recurrence function. And we did this. This is another experiment, and we found 3 periodic orbits in this particular experiment, for example, that came close to where they started at this level of relative error. Okay, and let's have a look at one of them, which is another video. I hope this is showing without latency. But the idea is, once again, I have sort of flow structure visualization of the velocity field on the right-hand side and the projection on the left-hand side. Of course, the projection is showing you a closed loop because this is periodic now. So the object is a closed loop, and the structures are still, showing these weird generation and disappearance of streaks that you just saw in turbulence as well. So, and we also looked at what happens when turbulence come close to these periodic orbits, and this is called shadowing, because we say that the turbulence shadows the periodic orbit for finite times, because when you see that the turbulence here on this projection is the black curve and the periodic one is the pink curve, and we see over and over again that for finite times, turbulence seems to be syncing with the periodic orbit. So the time evolution for a finite time seems to be possible to approximate by the time evolution on the periodic orbit. Here's another example where the flow structures are very similar for a short duration. And we'll have one last example in this video, which will show up soon. Here we go. Now the turbulence is slowly approaching. They are not synced yet, but let's wait. This is an interesting one. And now they are about to start moving together. Here you go. And as you can see, the visualization are very similar for a short amount of time, and this is the end of the video. But the observation that I'd like to make is that it seems that these episodes can be described by the periodic orbits, and then during this shadowing episode, these projections once again 3 dimensions are shown here, but these are in many more dimensions. And on these projections, these curves seem to have similar shapes. Okay, and this is once again almost qualitative, but we're close to getting quantitative in this description. So we asked ourselves, can we use this property? Can we use this similarity to actually measure these events without supervision? Okay, so without us looking at these projections, can we actually detect the shadowing from data analysis? And that's what and I'll sketch the steps of how we do that here. Okay, so we first start by having a library of projections where we capture the periodic orbits, and then here's an illustration of that, and we project our periodic and turbulent trajectories on these bases. And here's an illustration of that. The periodic is red, turbulence is gray, and we sample these trajectories. Next, we compute what is, oops, went too far. Now it's, yeah. Okay, next we compute persistent homology, which is a topological data analysis method. Okay, and what it does is it generates representation of these data sets at different resolutions and keeps track of the change in the topology of this set. And by doing so, you generate these diagrams that are called persistence diagrams, and they encode the shape information about the data. Of course, I'm not telling you how this is actually done, but what you should keep in mind is that you start with the data, you compute persistent homology, and in the end, you get these diagrams, and these diagrams encode shape information about the data in a quantifiable way. Okay, so then what you can do is actually define a metric between these diagrams, and here it's called the bottleneck distance. And it's not important what this actually means for this talk. Here's the reference where you can read about it. But what I'd like you to keep in mind is that now we have a number, we'll have actually 2 numbers that tells us the similarity between the data sets, between the shapes of the data sets. Okay, so this is the technical step. And using this bottleneck distance, we define what we call the shadowing distance. And then it gets contributions from the components and the holes of the persistence diagrams as a weighted sum. And then now we have the shadowing distance is the distance of turbulent trajectory at time t from the periodic orbit with the label I. So it's for every periodic orbit, we have a shadowing distance, which I'm showing you here. This comes from experiment, the simulation. Right? But when I say experiment, it's numerical experiment. Okay, and so here we're looking at time series, and then what we expect to see is that if this shadowing distance has a local minimum, there should be a shadowing event. And once again, illustrations as projections, as you can see, I'm showing 4 different minima. These first 3 I already showed you in the video. Here's the 4th one. And one important point is that, for instance, it's very obvious that in this projection, you can see the initial and final condition are pretty far away. So this is not a recurrence. This wouldn't have given us a signal in the recurrence diagram. But when we quantify the shape similarity, we get a signal, and it seems that our metric is working. Okay, this is another example of that, and so on. And so using this new metric, we define what we call the shadowing decomposition, which is essentially assigning a periodic orbit to a time interval by this simple algorithm. All we do is the first we search for the closest periodic orbit in the shadowing distance, and we check if it's closer than a threshold. If that's the case, we record our pair of periodic orbit and time. If not, we go next step in time and do this forever throughout our simulation. So this gives us a new way of thinking about turbulence time evolution as the sequence of shadowing events, which I visualize here in this bar plot, where each bar corresponds to a shadowing event. So we start at 17, we go to 5 and 12, maybe 11, I'm not sure, and so on. But we can now assign a periodic orbit to a time interval, which then gives you a description of chaotic time evolution like some kind of a Markov process, because exactly like a Markov process, because you basically have states in which you can find your system, and then transition rules in between. And I here showed that Markov process that is derived from the data in a network visualization. Okay, and we can also, of course, measure the transition probabilities of that Markov process from the data. This is a transition matrix of the Markov process tells me the probability of transition from periodic orbit I to periodic orbit J. So these are the matrix elements IJ, and this I can measure from the shadowing decomposition. And then this Markov chain, of course, has an invariant distribution. That's the left eigenvector of that Markov chain. Actually, in this visualization, the size of these circles are proportional to their the invariant measure of the invariant distribution of the Markov chain. In other words, as you can see, this distribution is not uniform. This is a distribution in the phase space in the system, and it's not at all uniform. And then using this invariant distribution, now I can define an average for the observables in my system. And this average is observables are the things that you're interested in a computational fluid dynamics problem, for example. And then here I'm showing you some examples of observables. These are kinetic energy, which is L2 norm of the velocity field, rate of dissipation, that's here omega is the vorticity field, so omega is the curl of U, okay, and then it's proportional to viscosity, and the power input is the energy that you put into the system. Of course, this has to be in statistical balance for the system to have some sustained long time process, right? And then in these pictures I showed periodic orbits and turbulence on top of one another on the planes that are defined by these observables. So here the energy and its time derivative, and I and D are power input and dissipation. And this is one last qualitative observation for you to see. Well, they seem to hang out in the same areas of these planes, but of course, we now have a formula to predict the mean values of these observables using the periodic orbits in our model, and that's what we did. And then here are two predictions using this expansion over the periodic orbits, where the weights come from the invariant distribution of the Markov chain. Okay, and what we do is we compare the numbers we get to our simulation, which I claimed that it was a black box because it had 100,000 degrees of freedom, and then the average is a time average in this case, which is just running simulations and then sampling numbers and then taking an average. And the two numbers that we get from invariant distribution and the long time average seem to agree. Okay. So, and that brings me to my conclusion, and I think I'm not too much out of time, I hope, but I'm done. So
you have maybe a few minutes on the...
Okay, the conclusion is that all this trouble was to give a description of the simulation in terms of number of variables that we can talk about. We can tell one another that there are periodic orbits where you can use a which you can use as a basis of time evolution of turbulence in this system. And and that's it. That's all I have to say. And if you have questions, I'll be very happy to address them. Thanks.
Thank you for a very nice presentation. Any questions or comments?
I can ask a few questions.
Hi. Yeah.
Hello. Thank you for the talk, Nazmi Hocam. So, first of all, you are trying to understand your system by looking at its phase space, right?
Yes.
Okay. And you're trying to find there certain loops, if I understood correctly, right?
Mm-hmm.
The periodic objects. And
yes,
these loops, although normally loops are one-dimensional objects, you're looking at certain tubular neighborhoods because of the
perfect. Yes.
Okay. All right.
Yeah. Yeah.
Then you're trying.
You can think of these areas as the widths of those neighborhoods.
All right. Okay. Nice. Okay.
You know, but you're on the perfect track. Yeah. Yeah.
Then you're trying to do some homological calculations. I don't know persistent homology, but roughly speaking, I guess the idea is to count holes again, right?
Yeah. Yeah. Correct.
Okay.
Yeah.
But you.
Think I should have had some backup slides for this one, but unfortunately I don't. But imagine having these points and then getting them fat. And so that's your continuous parameter, is the sort of radius of these points. And you get them bigger and bigger and bigger and bigger, and eventually those points begin to intersect, and then and you have a hole, or then those holes disappear, and so on. So that's what you get from these diagrams. Yeah.
Okay. But so this is not like the usual singular homology type of thing, then.
I don't know the usual singular homology type of thing, so I don't know how to.
Okay. So, but in general, homology, when you discuss homology groups, there are different type of homology groups, which are labeled by some natural number, which tells you different dimensional holes in a
perfect. Yes. We're just looking at 0 and 1.
Okay. Yeah, so 0 generally counts the number of connected pieces, and 1
exactly. So these zeros are the red dot points here. These are the number of connected pieces at a given resolution. Of course, at resolution 0, which is just the points that you started with, every data point is an connected component on its own. Okay, so trivially, and they keep disappearing because they keep merging. So that's what this part of the diagram tells you about.
Is there a way to look at higher homology and try to get some physical intuition out of it for the phase space, at least? I mean, like how these things work. Because if you were, so can I tell one more quick thing? So if you were in a two-dimensional system, for instance, would it make sense? Yes. If you were in a plane, it's not physical, but it's a toy model. Suppose you found some loops. Then these loops will be disconnecting the, they may be disconnecting certain loop paths which reside in the loop and which reside outside the loop. And maybe you would be able to talk about something like this. I'm not sure if you have chaos, because then this may not be the case.
In 2 dimensions, you don't get chaos to begin with. So you need at least 3 dimensions for things to get interesting. But
I don't know chaos that well.
No, that your question is absolutely valid in the following sense. In this particular problem, we have periodic orbits, and then these are the sort of sufficient. Sometimes this open office transitions are not great. Okay, so in 2 dimensions, when we look at periodic orbits, of course, we stop looking at topological changes beyond the one-dimensional holes, but you might imagine having much more complicated structures that you would like to not much more complicated, but higher dimensional structures, like invariant tori and so on, as your basis, and you can imagine situations where those would be the appropriate objects. And if you want to follow this methodology, then you should definitely care about the higher dimensional voids. Yes, that's
also by thinking about points as fat points. I mean, that has certain volume because they have certain radius. Then starting from a single fat point, you could have different vertices coming out of it, right?
This I don't know what do you exactly mean.
Because if you start from a single, like exactly a single point, then there's only a single path that crosses it, given an initial velocity. It doesn't make sense in the phase space. That point will flow to a certain direction, given an initial direction. But if it's a fat point, then you could have different velocities coming out of it.
Oh, perfect. Yep.
Okay, so you could have different vertices or higher dimensional objects, like. And you could maybe look at different homologies, higher homologies. And
yes, sure.
Just an idea. But one more quick question about the simulation. So simulations are quite particular objects. You give me a certain, for instance, geometry to begin with. I will be looking at this system living in a box or living in a sphere, maybe. I don't know.
Right.
So doing these particular type of simulations in different systems, can you come up with general statements that in general will be valid for most of systems with same properties, like viscosity around this much, so on and so forth?
Well, yeah, so there are universal parts of a turbulent flow which are usually discussed in terms of scales. For example, and that's sort of the old theory of turbulence, which is pretty nice, but it's only, for instance, if you have really tiny vortices that are very far away from the boundaries and then they're just doing their own thing, you can imagine that these like large length scales that you have in the system are irrelevant for these tiny objects. And if that's the case, then you get an universal properties for those parts of the system. That's true, and that's done. That's the roughly that's the Kolmogorov's theory of turbulence in 1941, I think. So these sure, but if you are taking the approach that I'm taking, it's likely that the methods might become not directly applicable in a different geometry and so on. So you would probably need generalizations along the way and come up with new techniques along the way. But that's why it's a very hard problem. So if you found the methods that solved all the systems at once, then maybe the problem is over. Okay, so we're not there yet, but we worked out one case where we can come up with a simple description, and then I think what's going to happen next for me is that I'm going to use this system as a test system for the new ideas. Okay. Because here is first system that I actually kind of know what's going on. This is it. To a large extent, there are missing pieces, but this seems to capture. This is a threshold dependent statement, but even the most stringent threshold choices, we get 50% of the time evolution covered by these shadowing events. And then, so this is a kind of a starting point for the next problem, actually. That's how I think of it. Yeah.
Okay. Thank you very much again for the answers and the talk.
Thanks. Thank you for the questions.
Can I ask a little question?
Sure.
Welcome, by the way. Nice to see you here. How did you detect the radius of these circles? I couldn't catch that.
Oh, sure. you do the data analysis and you infer a probability, the transition matrix. Those are the, this matrix Pij has elements, means that the probability of seeing a transition from I to J. Okay, so that's
what is the time range for this event?
arbitrary. Yeah, that's good question. So sometimes it happens immediately. Sometimes it comes back to itself after some time. So these are treated equally in this description.
Okay. I see.
Yeah. So we take everything, and then we find it. Of course, we have a lot of tests to make sure that this procedure gives you a converging distribution. Okay, so we change the thresholds, we change, divide our data sets into training and test sets and so on. We do a lot of tests to make sure that we keep getting the same distribution, and so the radius or maybe the area of these circles are proportional to their particular weights. Okay.
Okay, thank you.
Good. Thanks for the question.
Thank you very much for the talk again. We have a few minutes before the next talk, so maybe we cannot take any more questions, but thank you very much.
Thanks
and
a lot
especially it was very nice coincidence to see Gökhan's picture on the screen. He was, I think many of us know him from Mathematics Village or Boğaziçi University. It was we can send greetings to him from here.
That's Gökhan is the best outcome of my last talk in Istanbul. Okay, so he did a really great work, and yeah, thanks a lot.
Let's see what you get from today, maybe.
Let's hope. Yeah, I have high expectations.
Okay.
Thanks.